We are discussing about deadlock handling techniques. There are 4 deadlock handling techniques like deadlock prevention, deadlock avoidance, deadlock detection and recovery, and finally deadlock ignorance. Already we have seen something about deadlock prevention. In order to prevent a deadlock, there are actually 4 necessary conditions for the occurrence of deadlock in the system. The conditions are like mutual exclusion, no preemption, hold and wait, circular wait. These are the 4 necessary conditions for the occurrence of the deadlock. In order to prevent a deadlock, we should see that any one of these 4 conditions is getting violated. That we have already discussed. Now, let us see something about deadlock avoidance. The second deadlock handling technique is deadlock avoidance. Coming to this deadlock avoidance, first of all, let us see what is actually deadlock avoidance and how actually we are going to avoid a deadlock in the system. So this deadlock avoidance is a futuristic approach. So even let us try to understand why actually we are calling this as futuristic approach. Here in this deadlock avoidance, the system actually it maintains a database, and what actually the system maintains in the database is the set of processes which are actually trying to use the resources. So the system, it will be maintaining the database. In the database actually we have processes and as well as the resources. This information will be maintained as a database. Now the system in the sense kernel, so which is an important part of the operating system. So here the kernel, what actually the kernel will do is, if any process, if it requests for any resource, the process, if it requests for any resource, the kernel, so which is a part of the operating system, so what it will do is, so it will check whether that resource can be given to that particular process. And moreover, once that resource can be given to the process, the system or the kernel, it checks whether the system will be in the safe state or not. Let us try to understand what actually a safe state is. So therefore here what we are saying is, the system, it maintains a database. So in the database, what actually is there is the set of processes, so which are actually using the resources, and each and every process, so they will be declaring so how many resources it really requires and how many resources it actually requires in the future. So based upon this information, so the kernel, so it will be checking whether if any new process, so if it requests for any new resource, so the kernel, so which is a part of operating system, it checks whether the resource can be immediately given or not. So based upon whether if the system is entering into the safe state or not. So if the system, if it enters in the safe state, so then the system or the kernel, it will grant that particular resource to the requested process. If the system, if it doesn't enter into the safe state, so then the operating system, that is the kernel, so it will reject that particular requested resource for that particular process. So now here let us see how actually the system, it is able to tell whether the system is in safe state or not. So there are actually 2 different algorithms for avoiding a deadlock. So what are actually those 2 algorithms are? Resource allocation graph, that is the first technique to avoid a deadlock, and the second deadlock avoidance technique is Banker's algorithm. So let us see when actually the resource allocation graph is used and when actually the Banker's algorithm is used. So coming to this resource allocation graph, so this resource allocation graph, so it is actually used whenever the resource is having a single instance. So whenever each and every resource has a single instance, in such a case, resource allocation graph is used in order to avoid the deadlock. And when actually the Banker's algorithm is used is, so whenever the resources are having multiple instances. So in order to avoid a deadlock, and moreover deadlock avoidance is the second type of deadlock handling technique. And what actually this deadlock avoidance is, it is a futuristic approach in order to occur the deadlock in the system. so therefore here, in order to avoid a deadlock in the system, we have actually two types of algorithms. One is resource allocation graph and the other one is banker's algorithm. So as I have said just now, this resource allocation graph, it is used whenever the resource is having single instance, and this banker's algorithm is used so whenever the resources are having multiple instances. So let us see one by one. So first let us discuss about this resource allocation graph. So already we have seen something about this resource allocation graph. So in the resource allocation graph, so graph is nothing but it is collection of vertices and edges. So nodes are again consisting of processes as well as resources. So nodes can be either a process or a resource, and we have seen, so process is always represented with circle and node is always represented with a rectangle. And moreover, so coming to the edges, so we have two different types of edges. So whatever the thing we have discussed so far, so there we have seen that there are two types of edges. So one is the request edge, the other one is assignment edge. So request edge will be always from process towards resource, and assignment edge will be always from resource towards process. So far we have seen about these two types of edges. So now let us see the other type of edge, so which is nothing but claim edge. So claim edge is always from process towards resource, but this time we will be having a dotted line. If it is a request edge, it will be from process to resource, and moreover it will be a solid line. If it is assignment edge, it will be from resource towards process, and moreover it is also a solid line, so arrow will be pointed towards process. So these are the three types of edges. So the additional edge that is getting added here is the claim edge. So let us see what is the purpose of this claim edge and why we are using this claim edge, and how actually we are going to avoid a deadlock by using this resource allocation graph. So this time we will be having an additional edge, so which is nothing but a claim edge. So for us, let us see one example. So already we have seen something like a resource allocation graph. So here let us see the additional, so the extra edge that is getting added in this resource allocation graph. So here each and every resource, so currently in the system there are two processes P1 and P2, there are two resources R1 and R2. So and already we have seen that resource allocation graph, it is a technique which is used in order to avoid a deadlock when each and every resource is having single instance. So therefore here we have to assume that R1 and R2 now they are having only single instances. So currently this P1 is holding resource R1 and P2 is requesting for resource R1, and if we see, we are having a claim edge. So just now we have seen that a new edge will be added in the resource allocation graph in order to avoid the deadlock. So this is nothing but, so this is one claim edge and this is another claim edge. So here what is the meaning of this claim edge? So why we are adding this claim edges are, what is the meaning of this is, P1 it may require this resource R2 in the future. So that is the meaning of this claim edge. Similarly P2, so it may require this resource R2 in the future. So now suppose that, so as we have just now seen that P2 it may require this resource R2 in the future. So therefore now this P2 it actually requests for this resource R2. So as already it is a claim edge, so P2 now it wants that resource R2, so therefore it is requesting for this resource R2. So therefore, so this particular claim edge, so now it is becoming what is, it is becoming a solid edge. So now suppose that if this particular resource R2, if it is given, if it is allotted, if it is assigned to this process P2, so then the edge, so it will be converted like this. So suppose that, so if it is assigned to this process P2, so now in that case, so this becomes what is, this becomes an assignment edge. So now we can see here, so here this is a cycle. Okay, so here this is a cycle, so this is a claim edge. So the edges are from R1 to P1, from P1 to R2, again from R2 to P2, and finally from P2 to R1. So therefore from this we can conclude that here there is a cycle, and so this is an occurrence of the deadlock. So therefore here what actually the system will do is, as there is a cycle in the system, so it will reject that particular request, so which is from process P2 to R2. So that means it will not grant this particular request edge. So why? Because if it grants that particular resource to process P2, so there is a chance of occurrence of deadlock in the system. But here what is the main problem is, so suppose that here if this process P1, if it does not request this resource R2, so then definitely in the future, so here why we are drawing this claim edges, in the future this process P1, it may require this resource R2, so therefore we are drawing a claim edge. But suppose that this process P1, it never requires that resource R2, so therefore here this claim edge, so actually there is no chance of getting a cycle in the future also. So here unnecessarily what we are doing is, we are rejecting the request from process P2. So therefore here in this manner, as even though there is no cycle, even though there is no chance of occurrence of deadlock in the system, so unnecessarily, so we are not granting the resource to that particular process P2. So this is the main drawback of this. But anyhow, this resource allocation graph, so here we will be using this resource allocation graph in order to avoid the deadlock whenever each and every resource is having a single instance. So now let us see something about Banker's algorithm, so which is important, so in order to avoid the deadlocks. So let us see what actually this Banker's algorithm is. So let us see one problem for this. For understanding this Banker's algorithm, so we require a numerical example. So here what we are having is, we are having three types of data structures. So one is allocation, the other one is maximum, the other one is available data structure. So here the input for this algorithm, so anyhow we will be seeing what is the algorithm, so what is the code for this algorithm once we discuss this numerical example. But try to understand that the input for this algorithm will be the number of processes, so let it be n number of processes and m number of resources. So therefore this allocation matrix will be a 2 by 2 matrix, so as well as this maximum matrix will also be a 2 by 2 matrix, and similarly so this available will also be a matrix, so which actually it specifies how many number of resources are currently available in the system. Now here in this example, so whatever the example we are discussing, so here we are having 5 processes, let it be P0, P1, P2, P3 and P4. So this is the allocation matrix. And this is the maximum matrix. So let us see about each and every data structure in detail. So why actually we are using these data structures, and how actually we are going to check whether the system is in safe state or not. So this is an example. So here Coming to this allocation matrix, what is the meaning of this allocation matrix is, currently these many number of resources are allocated to this process P0. So as I said, we are having 5 processes and we are having 4 resources. So the resources are A, B, C and D. Now what is the meaning of this allocation is, currently 0 instances of A has been assigned to process P0. Similarly, 0 instances of resource B assigned to process P0. 0 instances of C are assigned to process P0, and similarly 2 instances of D are assigned to process P0. And coming to this maximum, what is the meaning of this maximum is, process P0, it requires 0 instances of A, 0 instances of B, 1 instance of C and 2 instances of D in order to complete its execution. So during the lifetime of execution of process P0, it requires these many number of maximum resources. So what we are saying this as maximum resources. So it may require 2 instances in max, or sometimes it may require only 1 resource and it can finish its execution. That is the meaning of maximum. And now coming to this available, after we assign the resources like this, so after we assign resources to process P0, P1, P2, P3 and P4, so these are the number of instances that we are having. So that means these are the leftover resources. So for A we are having 1 instance, for B 5, for C 2 and for D 0. So this is the data structure we are having. So now here we need to check whether the system is in safe state or not. So how actually we are going to check this is, in order to tell whether the system is in safe state or not, we have to find out the safe state sequence. So let us see whether we are able to generate these types of safe state sequence, the Banker's algorithm. What is the output of this Banker's algorithm is, so the algorithm, it has to check whether such type of safe state sequence is there or not in the system. So for this we have a procedure. So let us see what is that procedure. So here what is the first step is, first we need to calculate what is the need matrix. So let us see what is the need matrix. Need matrix is also a 2 by 2 matrix. So what is the meaning of this need is, so if you take this process P0, we need to calculate this need matrix for each and every process. So therefore if we take this process P0, already these are the resources that have been assigned for this process P0, and at max it requires these many number of resources. So therefore what is the need, still how many processes that process P0 require in order to complete its execution. So how actually we need to calculate that is, so need is equals to, so how actually we are calculating this need is, so whatever the process it may be, so this is how actually we will be calculating this need. Need is equals to, need of I is equals to max of I minus allocation of I. So here I is nothing but the process number. So I is nothing but the process number. So therefore based upon this formula, let us try to calculate, so what is the need of this process P0. So coming to this need, so here for process P0, so as I said, need of I is equals to max of I minus allocation of I. So therefore here need of process P0 is 0, 0, 1, 2 and allocation is 0, 0, 1, 2. So therefore 0 minus 0 is 0, 0 minus 0 is 0, 1 minus 1 is 0 and 2 minus 2 is 0. So this is the need matrix of process P0. So similarly, so if we compute in the same manner, so again, so suppose that if we take process P1, so what is this max? So max is 1750 and allocation is 1000. So therefore if we calculate, 1 minus 1 is 0, 7 minus 0 is 7, 5 minus 0 is 5, 0 minus 0 is 0. So this is the need matrix of this process P0. Let me write the need matrix for other 3 processes also. So this is the need matrix for each and every process. We need to calculate for each and every process. After we calculate like this, so now what we need to check is, we need to, so as we have seen just now, the intention of this Banker's algorithm. So the final output of this Banker's algorithm is, So we need to generate, we need to check whether there is a chance of safe state sequence or not. So if we get a safe state sequence, so then we can say that so the system is in the safe state. If the system is in safe state, so then there is no chance of occurrence of deadlock. And if the system, if it is not able to generate such type of safe state, what is the meaning of that is there is a chance of occurrence of deadlock in the future. So now let us see how actually we are going to check whether the safe state sequence is possible or not. So for that, first let us start with process P0. So the first step is, so we need to check whether this is the need of process P0. We need to check whether this is less than this available or not. So here this is the need matrix, and we should check whether with available resources, with these many number of available resources, whether process P0 is able to finish its execution or not. Yes, so definitely it is possible. So therefore the safe state sequence, it can start with process P0. So even similarly we can check for whether any other process can start the safe state sequence or not. So if we check for process P1, so here 0 is less than 1, but if we see this 7 is greater than 5. So therefore here, as it requires 7 instances of B, but currently there are only 5 instances of B, so process P1, it cannot start its execution. So therefore definitely P1 cannot be taken for the safe state sequence. So now similarly, so we can check for process P1. So if we check for process P1, we are facing the same problem. So if we see this D resource, actually it requires 2 resources, but for D we are having only 0 resources. So therefore even, so we cannot take this process P1. So now similarly, so let us see for this process P3. So if we take this process P3, so even we can take this process P3 also. Why? Because the need of this process P3 is definitely lesser than this available. So therefore even the safe state sequence can also start with process P3. And one more important note that we have here is, we can have n number of safe state sequences. So it is not like we'll be having only one unique safe state sequence. We can have n number of safe state sequence. So therefore the safe state sequence, it can either start with P0 or even it can start with P3 also. So therefore let us start with process P0. So if we start with process P0, so what is the meaning of this? So we have assigned, that means process P0, it has started its execution and it has completed its execution. So therefore after it has stopped its execution, it is releasing its resources, and whatever the resources that are currently allocated to this process P0, so now they have been added to this available matrix. So therefore 1 plus 0 is 1, 0 plus 5 is 5, 1 plus 2 is 3, 2 plus 0 is 2. So here what we have done is, process P0, it has completed its execution and it has released its resources. Whatever the resources that have been allocated for this process P0, we are adding those resources to the current available resources that we have in the system. So we are having a data structure. We are getting the data structures like 1, 5, 3, 2. So this is the current data structure for this process. That means these are the number of available resources that we have in the system. So we have started with process P0. So now let us see whether any other process request can be satisfied with these available number of resources. So again, let us take for this process P1. So again we get the same problem. So here it requires 7 resources, but here we have only 5 resources. So therefore let us not take process P0. So therefore let us see whether we can satisfy the request of process P1. Yes, definitely we can satisfy the request of process P1. Okay, so why? Because so 1 is equals to 1. Okay, that means need is equals to available. So even need, so here it requires 0 instances of B, but here we have 5. Here we have 0 instances. It requires 0 instances of C, but here we have 3. And here it has 2 instances, but here we have 2 instances. So therefore definitely we can give the resources, the current available resources to this process. Sorry, this is P2. So we can give the current available resource. Current available resources can be given to this process P2. P2 also completed its execution, and therefore whatever the resources that are allocated for this process P2, so we are going to add to the available resources. So therefore it will be 2, 8, 8 and 6. So therefore, so these are the current available resources. So now again we need to check whether any other process request can be satisfied. So we can give the current available resources to process P3. So therefore, again whatever the resources that have been allocated to this process P3, again we are going to add to this available. So 0 plus 2 is 2, 6 plus 8 is 14, 3 plus 8 is 11, 2 plus 6 is 8. So these are the current available resources. So now if these are the current available resources, so again let us see whether any other process request can be satisfied. So here if you observe one thing, either we can take process P1 or else we can take process P5 also. Why? Because so both of these process requests can be satisfied. So we can take in either fashion. So let me go with this process P4 itself. So therefore P4 has completed its execution and even it is releasing its resources. So therefore 0 plus 2 is 2, 14 plus 0 is 14, 11 plus 1 is 12, and here this is something like 4, so 4 plus 8 is 12. And finally after process P4 completes its execution, so we are going to give the resources, the available resources to this process P1. So even P1 also completed its execution. If that is the case, so we will be getting like 3, 14, 12, 12. So therefore, so this is how we are going to generate a safe state sequence. So here these are the total number of resources that we have in the system. So here one thing we need to remember is whether whatever the count here we get, whether this is equal to the total number of resources that we have in the system or not. How actually we are going to check that is, so initially in order to check, so we need to add all these things, 0 plus 1 plus 1. So it is something like 2. And this is something like 9. So this is 8, 11, 12. So here we are getting this as something like 12. So therefore here what actually we are getting is, so the total number of resources, so this is equal to the resources that here we are getting as a, and one more important thing, so here once we add this, we need to add this to the available resources that are there initially. So actually we have performed all these type of calculations, but before itself we can check what are the total number of resources that we have in the system. So for that what we are doing is, so we need to count, we need to perform, we need to add all these values that we have in the first column. This is something like 2, 9, 12 and 12. Whatever the value we get here, so that should be added to the current available resources in the system. So it is something like 1520. So if we sum up, so what actually we are getting is, so I am erasing this. 2, 9, 12, 12, the current available resources. That means before we try to find out the safe state sequence itself, we need to calculate the total number of resources. So we need to add these values 1, 5, 2, 0. So what actually we are getting is, so we are getting something like 3, 14, 14, 12. Sorry, here this value is 10. By mistake I have written as 12. So therefore here we are getting it as 10. So 10 plus 12 is 2 is something like 12. So here if we see something, so this value is equivalent to this value. So therefore even though after we generate this safe state sequence, one thing we need to check is whether the total number of resources. So how we have calculated the total number of resources are, so we need to add each and every column we have here, we are getting 2, 9, 10, 12. This should be added to this value, so it is something like 1520. So once we add whatever the value we get here, so this should be equal to this particular value. So once we get this, then only we can conclude that the system is in the safe state sequence. So once the system is in the safe state sequence, what is the meaning of this is, so there is no chance of occurrence of deadlock. So here the resources can be given to the requested processes and we can complete the execution of all the resources. So here in this manner we are going to avoid the deadlock. So let us see how actually we are going to write the algorithm for this. So step 1 is, so this is a algorithm for this is a code for bankers algorithm. The step 1 is, we are taking the input. So what is that input is processes and resources. Processes are n, resources are m. That is the first step. So after we see that, after we take that input, so next we need to take two data structures. What are those two data structures are? It can be any of these two data structures like max, need, allocation. So in our previous example, so what are the two types of data structures we have taken are, so we have taken max and allocation. So based upon that max and allocation, so we have calculated the need matrix. So we have taken max, allocation, based upon that we have calculated need. So how actually we have calculated that is, need is equals to max minus allocation. So either we can take max and allocation, we can calculate need, otherwise, so what we can do is, so we can, so sometimes it may happen that all depends upon the values that are given in the problem. So sometimes they may give max and allocation. In that case we need to calculate need as we have seen in the problem. Sometimes it may happen that they may give allocation and allocation and need. In that case we need to calculate max. How actually we are going to do that is, we need to just sum up this allocation plus need, we will be getting the max. So sometimes, so what actually they may give is, they may give max and need, then in that case we need to calculate allocation. How we are going to do that is max minus need, that gives us what? Allocation. So that all depends upon the problem. So here whatever the numerical we have seen, so they have been given for us max and allocation. Based upon that we have calculated the need matrix. So then after that, the third thing that is required for us is available resources. So they may give any one of the two data structures like either max need or max allocation or need allocation. So based upon that we need to calculate the other data structure. So just now we have seen how we are going to do that. So then they will also give us what are the available resources, current available resources in the system. So then the next step is, step 3 is what is, we need to take a flag variable. So the flag of all the processes will be initially made 0. So that is for all the processes from 0th process till n-1 process, flag of I will be 0. So then we need to find out what is, we need to find out need matrix. So that is need n of m. So what is the meaning of this is, so the size of need will be what? N by m. So here n is number of processes, m is number of resources. So already we have seen in the example how actually we are going to calculate that, and the formula for that is max n of m minus allocation n of m. So this is the third step. So whatever the thing we have done, whatever the procedure we have done there, so we are writing the same thing in the form of the algorithm. The first step is we are going to take the number of processes as n, the number of resources as m. We are assuming processes as n and resources as m. Then we are taking any two data structures, whether it is max need or need allocation or max allocation, we are calculating the other data structure. So then we are taking the available resources also. The third one is, so we are going to make the flag of all the processes as 0. So we shall see what is the purpose of that. So then, and moreover, so it should be done for all the processes. Then we are going to calculate the need matrix. So let us see the fourth step. So what is the fourth step is, we need to find, so which process can be taken for starting the save state sequence. So therefore the step 4 is, so find a process Pi, such that flag of I is 0, flag of I is 0 and need of I is less than or equals to available. So this is what we have seen. So we need to check whether there is any process whose flag is 0 and whether the need of that matrix, whether it is lesser than or equals to the available number of resources. If that is the case, what we need to do is, if such I exists, so then what we need to do is, we need to make the flag of that particular process as 1, and the next step is, we need to update this available data structure as available equals to available plus allocation of I. So whatever the thing we have done in the problem, we are going to represent the same thing in the form of steps. So then go to step 2. So what is step 2 is, again we need to find another process. So this is actually step 2. So again we need to find another process such that whose flag is 0 and whose need matrix is less than the available matrix. So just now we have updated the available matrix. So this will be the recent available matrix that we have in the system. So we need to repeat this process, so until we get the save state sequence. So here, after we get the flag of all processes as 0, after the flag of all the processes is 1, so then, so for all I, if flag of I for all if flag of I is 1, so what is the meaning of that is, the system is in safe state, otherwise the system is not in the safe state. So here in this manner, by using this Banker's algorithm, we are going to check whether the system is in safe state or not. So if the system is in safe state, so then we are going to grant the resource to the requested process. So otherwise we are not granting the requested resources to the requested process. So this is the Banker's algorithm. So in the next class, let us see about deadlock detection and recovery.